that we were talking about the linear classification model, like logistic regression and softmax regression. And we saw that these are examples of empirical risk minimizations with a certain loss function and effectively a linear function for the logic states. And so these would lead to linear classification boundaries. So in the case of logistic regression, binary classification is really simple to see. In the case of softmax regression, they're going to do it in a homework problem. If you start from the softmax regression model or multinomial logistic regression, you can find out the optimal rule, and they separated the basically regions that separate the classes of the optimal rule or optimal or base rule would be lines or isoplanes in general, and then the intersections would be these polyhedral sets. So you would get like one class is here, the other class is here, and so on. And so if the situation is more complicated, basically the classification boundaries are somewhat linear. So the boundary between two classes is linear. And so if you have a nonlinear classification boundary like this, or even worse, like you have things that are inside a circle and the other class is outside, then these models, as they are, they're not going to be performing well, because let's say if I do a logistic regression in this case, I start like dividing the space into these type of regions. No matter what I do, I'm not going to have a good misclassification rate or accuracy. Okay, so there are extensions that we can easily make. One is via feature maps that I'm going to talk about hopefully later. It's very simple. The other one, which is very popular nowadays, is via these so-called neural networks. Neural networks are nonlinear parametric models. So you, for example, basically replace this function here, which is a linear function. So it takes xi massive linear into output, replace it with a parametric model that's nonlinear. And the idea of neural networks is we just introduce very simple nonlinearities and then compose. So the idea is, so let's just select the second idea. Second idea, neural networks. So introduce say component wise nonlinearities and compose. So that's the basic idea. Okay. So what I mean, so if you think of a simple function, linear function, we saw that it can be written like that. Or if you want to be in the language of machine learning, it would be like W, I usually write it like that. So X is 1 and X tilde. So that's the feature. So there's a late matrix of playing with the actual features, and there's a bias or intercept. I usually like you've seen this is a particular feature map. Okay, so you map X to different states. In this state, I have like a fixed feature of 1, and it's still that is my original feature. So they usually work with these, if you recall. So let's stick with that. So this is a linear map. The way people make it nonlinear is they apply nonlinearity to each coordinate. So let's say if I had, for example, my so sigma function that we had, the sigma is a particular nonlinearity. But if I like, let sigma be a general nonlinearity, so it's like a map from R to R. Okay, so this could be, for example, usually you want something that's okay, so it could be like sigmoid, for example, it could be our own original sigmoid. Okay, that's a nonlinearity that maps from R to actually 0 to 1. We could have a nonlinearity that maps from like this, so maps 0 to like negative to 0 and then positive to positive, like basically identity. So this map. This is very common. This is called ReLU, rectified linear union. So it's almost like a linear function. So linear here is linear here, but overall it's not linear. It's sort of there are other examples. So there's the tanh, tangent hyperbolic. There is leaky ReLU and gemline leaky ReLU and stuff like that. But for us, it's just some sort of nonlinear function. So what do we do with that? So you take the this function. Okay, so this produces. So suppose the input is so x belongs to Rd. Okay, and then we want to map it to. So in this case, theta x maps things to, let's say, R. In our case, it was RC. So the number of classes. What I'm going to do is that I'm going to apply this on each element of this thing separately. Okay, so I get sigma, let's say theta x1, sigma theta x2, dot sigma theta x c. Okay, so this is a new vector. Okay, now I'm going to call this my new function. Okay, so this belongs, like this depends on a parameter. And then I have this external in here. Okay, so you apply this to each element of the function. If you want to be simple, I might write something like sigma theta x. So this is understood to be applied to each component of the vector because it's univariate. Okay. So now this is going to be sort of nonlinear. It's not the entire story. So what you do then is you most likely have more. So I have this. Now I pass it to a function that looks very similar. Okay, so for example, I have this version. And then I have another one, which is f theta 2. This looks very similar. So it takes an input, theta 1. Let's call this maybe z, for example, because it could be in a different domain. And theta 2 takes it and then applies linearity. Then I compose these two functions. So let's say z in this case. So this belongs to, let's say, RC. Then the input to this would be in RC. The output could be in RC, for example, or some other domain. So I'm going to compose them now. So I do f theta 2, f theta 1 of x. Okay. So now I have a new function, which we can call like g if you want. Depends on these two parameters. And this really is truly nonlinear because of the nonlinearity is here. And the nonlinearity is here. When I compose, I get something which is not represented by linear. So this is really like sigma theta 2, and then sigma times theta 1 x. I have two parameters, and this is the end of the story. Yes.
We use sigmoid because it is smooth, right? Relu is not.
This is not a smooth. So this, whether you want to use the smooth or not a smooth, is not something that you're gonna worry too much. Both work. This was very popular. The smooth ones are also useful. The smooth ones are useful because at least theoretically the derivative is like everywhere differentiable. Okay. And you hope that the smoothness will help optimization. But I mean, there's no reason why necessarily this is preferred over that. So this is very popular. Useful. One reason why it's popular is it's very easy to calculate. Okay. So I either check the sign, either zero it out or capacity.
For this class, what do we define the derivative at zero?
Undefined. So this matters if you end up there, but I actually don't know what they do in PyTorch, so you should check it, but what they do, but arbitrary, so it's defined arbitrary. There's a left derivative, zero, there's a right derivative, one. You're hoping that you're not gonna get stuck there, so you're hoping you'll either like here or here. If you have done like convex optimization or L1 penalization, L1 penalty looks like this. So you know that this not differential, like this point of non-differentiability matters. So a lot of action happens here because when things are here, usually good, like the coefficients are zero, so it allows you to have non-zero coefficients. And then there is a self-differential here. So there is something which is called self-differential, and self-differential can be anything between -1 and negative. So these functions are self-differentiable. And anything in this case 0 to 1 works. And you really want to do subgradient descent. But people don't care about this. So technically anything in 0 to 1 works. So these are convex functions and self-differential and subgradient descent conversion. Like the thing of convex. So if you want subgradient exists at 0, but you don't care too much, so it belongs to 0 to 1, anything 0 to 1. The subgradient is like the slope of any line that passes through this and it's below the function. So any it's like extension of tangent. So there is no tangent here, but there is supporting half. And the supporting half plane, you can change the slope from 0 to 1, and it's below the function, it's good enough. And you can move in that direction. Good point. Okay. It would be interesting to see what they do choose PyTorch with the gradient. And the other question, yes.
Why are we wanting to compose it to simple nonlinearity instead of introducing a direct bigger law of nonlinearity?
So the simple nonlinearity is applied coordinate line, so then there's this linear map, right? And then I apply coordinate line. So generating like a general nonlinear function is hard. Okay, you can do that, but then you move away from neural networks. It's possible to have a general nonlinear function, okay, but proposing a class of general multivariate nonlinear functions is not easy. Okay. So nonlinear functions in high dimensions are like the space is very big. Okay, so you want to have some sort of a restriction on the class of nonlinearities that you're going to generate, and this produces a nice restriction. So here we just have two parameters, like introduce two matrices. That's the number of parameters that you introduce, and you introduce nonlinearity. Okay, so if you, for example, you can have, like I can have like theta 1 x and then pass it to a general nonlinear function. This belongs to some function class. This also works. Assuming, for example, like let's say that, I mean, it would make sense if you have, for example, this is C by D. Okay, let's say if D is much larger than C, then it might be possible. So let's say C is 3, D is like 50. Okay, it might be possible to come up with a good two-dimensional nonlinear model for G function class. But if, for example, this is 50, this is 20, I still need like a 20, like a nonlinear function defined on 20-dimensional space. And so we can define these things, it's fine. But controlling the complexity would be harder. And traditionally, you would go there. But at some point, you just say, okay, so why do I need theta 1? I'm just going to go G of X. G belongs to some general class of functions. So the more abstraction you introduce here, the more restricted the class is, and hopefully you can like control. Okay, so hopefully, if the actual function looks like this, then starting from this is better.
Because of the tractability.
Tractability and like from a statistical perspective, it's a simpler class. This is simpler than maybe like all the Lipschitz functions. On order.
And theta is applying to all the coordinates of it.
Yes, yes. So the way that people usually, by the way, this is usually called multi-index model. And it is popular, like classical statistics, where G is more general. But okay, so what this looks like, usually what people do is you have the input X, and they write it like this. So if you see like some of these diagrams, traditional diagrams, you have X1, X2 up to XV. That's the input vector. And then you have, let's call these Z. In this case, for example, let's say there are 3. You get Z1, Z2, Z3. These are hidden units. So these are input units. And then you'd see like people, so this like Z1 takes all these in. This guy takes all these in. And this guy takes all this. Okay, so you'd see things like that. So this is saying, for example, Z1 is like a linear combination of all the other ones. Okay, so theta 1, let's say dot times X. Okay, and this is theta 1 dot or 2 dot X. And this is theta 3 dot X. Or if you add the sigma, this would be like actually the sigma of this. Okay, so these are the hidden units. And so this is not the fully connected layer. Fully connected because everything is connected. So you can introduce sparsity, but this is often done in an ad hoc way during training. Potentially, yes. Okay. And so this is one layer, this is the hidden layer, and then you have the next stage. In this case, would have like the same, because I took the C's here the same. So we would have like this is the output layer. So every one of these would be connected to every one of these guys. And I realized that I made a mistake. So this is theta. Let's call this theta 1 maybe. I'm going to call this theta 1 like this. And then there's a theta 2. So there's a theta 2 that controls these control weights. So these are all like this gate, you like weights, each one of these with a certain weight, and then check. So each one of them is called a neuron. So you want to blow it up. So you have Z1, Z2, Z3. And the other reason why people do this is this like inspired by the neural network of the brain. So these are called artificial neural networks. And apparently you have one in your head, which is inside your brain. And so they looked at the neurons, and neurons apparently do this. So they take a linear combination of the inputs. So each neuron is connected to a bunch of other neurons. So this is, I'm gonna call this Z tilde 1. This takes input from these and weights them in a way. So it takes, for example, I don't know, let's call this. If you want to be like in the theta domain, it would be, okay, there's a bias, so ignore the bias. So it would be like theta 1, 1. This is the second layer, Z1 plus theta 1, 2. Z2 plus theta 1, 3, Z3. Okay, there's just some weights. And every neuron will do this, and then you apply nonlinearity. So that's the job of a neuron, at least. This was the understanding of what neurons do at the time that these were invented. Maybe like neuroscience was diverse. I don't know what I'm to say that understanding of neurons is, but this was at the time. And they had like these electrical potential, and like there's like basically electrical signal. So it's like a gate. So it like calculates the linear like combination of the inputs and then gates it. So there's a gate. So if it's bigger than a threshold, it will pass through it. And that's why, for example, the red is very common. I mean, I'm ignoring the intercept here, but if you imagine the intercept and if you have the redo, this intercept allows you to like shift the location. So if this value is bigger than a certain value, let's say this was minus, for example, 2, and if sigma was the ReLU, and this is bigger than 2, it would pass through to the next layer of neurons, otherwise it would shut off. So just for your own sake, just remember that there is usually a bias in that neuron for some mistake. It's like some B here, B2, 1. And these would be W. That's W better, right? That's W. Weights, okay. And then the combination of W and B is what it's called. Is that sort of clear? So there is history, there's like inspiration from nature. There is theory that these like maybe 2-layer neural networks can represent any reasonable function. Within like epsilon degree of accuracy, you increase the number of neurons. It's a 2-layer neural networks are so-called universal approximate approximating function. But you need to increase the number of neurons. And you need to nonlinear. Okay? Yes.
What is the 2 included in the parentheses?
So that's the second layer. I'm putting it 2 for the weights and biases of the second layer. So this parallel. So this one would be like theta 1 as I written. So it's like theta 1 here and theta 2 here. Okay, so you can think of this as like including weights and biases. Weights and biases. And there's a website called Weights and Biases. Collect the weights and biases. Like a startup to help you like store your weights and biases. These are like sacred now. So you have the weights and biases of like a giant network, you can make money. It can be like a company that just generates stuff. So people train these, and then if you have the architecture and you have the weight, then you have the function. So these are now like the goal. I don't know what to call it, but just very sought after. So if you have a good model, and if I know the architecture, I can pass through the weights and biases, and you don't have the function, you can just do whatever you think. Give it input and it produces output. You can have like your own chat GPT. So these are like static model. So it's like just the function from input to output, and then They're described by these weights and biases and a particular architecture. So there's this architecture. In this case, the architecture is very simple. So you have these linear layers, and in my case, like I have two linear layers. And usually there's a nonlinearity which you don't represent, but let's say there's a nonlinearity here. So linear nonlinearity, let's say, I don't know how should I write it, but nonlinearity and then linear layer. Nonlinearity and out. Okay, so this is the architecture of my model. And I just have to give you the dimensions. So the input, for example, is D. In our case, this was C. This was C, and I think this is C as well. Okay, now this can represent, so this can replace whatever we had, for example, before we had just a theta linear model from D to C. And this was here. So it would like used to be like f theta of xi was just theta of xi. Now I can just replace, so this is modeling the logics, okay, the generalized logics of the classification. And so now I just replace it with my new neural net. So any function from RD to RC can be interpreted as producing logics. And so these are the things that after I apply softmax, we can probably use a test. Okay, so if you want to have the full model is for multi-class classification, there's a softmax layer as well at the end. It takes the softmax and it produces a label. But if you recall, we like absorb this into the box. So my new like nonlinear model is now this, okay. So I have this architecture, I can use like the weights and so this particular architecture is called multi-layer perceptron layer, but multi-layer. Layer perceptron. So the third reason, like the generalization of the perceptron algorithm. But this is two layers that can add more layers. Okay. So we have the input layer, the hidden layers, and then the output layer, and define it however you want. But generally speaking, there are multiple hidden layers that process the data, and then there is the output. Usually, the output of multi-class classification is before you apply the softmax is like a number of tests. So you see that logics. So logics in this case is whatever goes into the softmax to your problem. And this can be anything. There's no restrictions to the 0, 1, 8, 7. Sounds good. These are also called feed-forward neural networks. In contrast to like recurrent. So there is no information flowing backward. Just you process and then move forward and back. So what are neural networks? In one word. Sorry. There are parametric nonlinear models. Okay, if we add a few more words, there are parametric nonlinear models that are constructed by composing linear functions with like component-wise nonlinear. Okay, that's the whole sort of. And they have been very successful, like this, combined with the ERM framework, and the fact that you can use gradient descent. So gradient descent would be very easy in these models because I just need to calculate the gradient. And because it's a composition function, we have a chain rule. So if I know how to go back to your just the chain rule in calculus, right? This is like univariates. If I want to take the derivative of something like that, right? If I take the derivative of this, it will be just f prime t g prime ft. Okay, so I need to be able to calculate the individual gradient and then sort of compose and then also this product. And the same goes with multivariate. When you go to multivariate, when you compose, it's easy to calculate the gradient if you know the gradient of the individual elements. And individual elements are really simple. So linear combined with these nonlinearities, so it's really easy to differentiate. So you can compute them, depending the derivative is very easy to calculate. Conceptually or symbolically. And then so you combine, you have the loss, you have the empirical loss, you plug in this parametric model, you initialize, you do them to the same. And you have a model that fits it into the data. And then you tweak, then you change the number of layers, the dimensions of the hidden unit. So there's no reason why this should be C. This could be, for example, H1, and this has to be H1, and then the output is C. If I add more layers, I can change the dimension. Like how many hidden neurons do I want? I could go like from big to small to back to big, or I can like do different things. I can do like they go like that, and then that, and that, and then come back. So anything that you can imagine, so you can play with and then figure out what particular problem, what works. We're not going to worry with space. Yes.
So when we are increasing the dimension or decreasing the dimension, what exactly are we doing?
Exactly. You're just like defining a new class of functions. Okay, so increasing the dimension or decreasing the dimension just changes the nature of the class. What exactly happens, I don't know. Okay, so what happens when you like concatenate all of them together? So, for example, like go from dimension like 50 to dimension 1000, you introduce a lot of parameters. So you have usually that's what people usually do. I mean, I think it depends. So you have to like check what actually works. So this is very like it's like a combination of art and like science. So what you can look at what people have done and what worked, and then you can sort of try to read what they increase the number of parameters. So when you increase the dimension, you increase the number of parameters. And so whether this is good or bad, it's upward debate, but oftentimes people increase and then back decrease. So
When we are increasing dimension, does it mean that we are extracting more information from the data?
That's where I can't say anything. You just increase this, so you have more hidden neurons. That's it. That's as far as I can tell. Whether you extract more information or not, it's just a new existing function class. And potentially, if you have more parameters, the function class is richer, but that's also not obvious. So if you add a lot of parameters, it's not clear how the complexity of the class grows with the number of parameters. So you can have like billions of parameters, but the function class might like actually behave like something which has like a million parameters, independent parameters, because all the nonlinearities things could potentially cancel out. Okay, so you can have like a lot of these neurons could end up not affecting much because subsequent neurons, let's say if you have residue, it could be in the end, like when, for example, you fit the model, it could be that the regions are aligned such that this neuron never sort of gets anything to the output. Okay, so it like falls within like the region which is flat, like zero out by other neurons. So you could have like removed it from the flat. But this part is not very well understood and it's hard to understand, but increasing these apparently leads to easier optimization. So you over parameterize, you like make it very big in the middle, And it fits the data better, so you can optimize better. Then the question is that, okay, I have a lot of parameters, maybe I'm overfitting, but then overfitting is not as severe as you would have imagined. We haven't talked much about overfitting. You saw like a glimpse of it last time. If you have just a softmax model and sample size is very small, the sample size is very small, this would be a lot of parameters, and over the training loss would go down much faster than you would expect, for example, with the 1,000 sample versus the 20 sample. But that does not necessarily mean that you're doing better classification for future. Okay, so there's this issue of the balance between overfitting and ease of optimization. But it seems like these people in PhD have found out that these over-parameterized networks, at least like if you have a giant data set, and if you over-parameterize, they can like the gradient sentence optimize very well in certain applications. The applications that you hear that have been successful, let's say in the vision, in the language model, these have worked very well. And that's as far as I can tell. Okay. There.
In the multi-layer perceptron diagram, what is the meaning of like the filled square, the square?
The square, I'm just, this is not the standard notation. I'm just putting this here to emphasize that there is a nonlinearity. So you can think of it as it should be perhaps like better to write it like this. So there is this nonlinear layer. So everything that passes through coordinate wise, you apply this nonlinearity. So it's like sigma, sigma. The same goes here. So without this, if I remove this, it's just going to be the composition of two linear maps, and a composition of two linear maps and another linear map. Okay, so we can pass the linear model. So this simple addition of these pointwise nonlinearities would reduce the function. If you remove these, although it would be linear, the parameterization would be different. So that's another cool interesting feature. For example, if I do this, so this happens a lot in neural networks without people much realizing. If I remove the nonlinearities and I have like gone from like a higher dimension to a lower dimension, let's say H, that's my linear model here, no nonlinearity, and I go back from H, for example, to C. This is again a linear model because we would like the product of two matrices, let's say theta 1, theta 2. So X goes to output, the output would be theta 1, or theta 2 times theta 1 times X. Okay, so which is the new theta. Just the product of two matrices. But the idea is, okay, so let's do maybe A and B. So this is A, this is B. I first apply A and then I apply B. So my function is really BAX, which is some other weight if you want, or theta. But the thing is, I have parameterized this linear model as a product two other matrices. And so this in particular restricts the rank of the transformation. So the rank of a like a BA, for example, yeah, so B is like C by H, and this is H by D. So what is the maximum rank of this? Let's say H is much smaller than B and C. The rank of BA.
H.
Yeah. So when you have a product like this, this inner dimension controls the rank. So the rank of this linear transformation is H. So if you have a general linear transformation from B to C, the rank could be at most the minimum of the two dimensions. But by this procedure, you restrict the rank. Okay, so this would be a low rank model. So even without the nonlinearities, there is something interesting going on if you change the dimension. If you increase the dimension, it's not going to affect. So if you go from D to something bigger to something like C, that model will have, can model all the full rank possibilities, all the possible ranges. But if you do something like that, we restrict, so this would be a low rank model.
So what is the meaning of a low rank?
So there are a lot of interpretation in other contexts, but in this project, in this setting, it's just like a way of reducing the complexity. So the space of low rank images is smaller than the space of all linear transformations. The linear transformations from C to D that are ranked S are is a smaller. There are a lot of interpretations maybe we talked about later later, but in this case, okay, so you could, for example, write it. So maybe let me actually. So if we go from like D, what is the interpretation? So if I have, for example, let's say A1 dot up to A. H dot, and then I have B1 dot up to very. So let's say it's just H is 1, okay. So you have B, and then you have, I'm going to write it as A transpose. So this would be 1 by D. This would be C by 1. Okay, so this is the extreme case, which would be a rank 1 transformation. This is basically saying there is this matrix A, so I multiply this, there's this feature, A transpose X, that I construct, and then all the classes are dependent on this feature, this single feature. So all the the probabilities are just rescaled multiple of this. Okay, so there's really one feature that's affecting all these classes. And then you can generalize, there is this reduction in complexity. And in general, you could have different, probably different classes could depend on different linear combinations of X. Okay. In this case, for example, we're just modeling it. In this case, it's a little bit tricky, but just one feature, one transformation, one transformation input, you just restate it, gives you all the properties. Okay. If you think about this, this is a very simple sort of model. The full general linear model from B to C is saying that each of these potentially depend on different linear combinations. The more general model would be basically A1 transpose X up to AC transpose X. Okay, so that's the more general linear. So the probability or the largest of each one of these classes depends on the different feature. This thing are scaled multiple the same feature. There are more interpretations in the case think of the latent variable. So okay, so this is a very simple, it's a very simple neural network. If you remember again, I'm just showing you these to get familiar with this PyTorch way of doing things. So you have this again NN module, Torch NN, and then the Torch NN functional, and then this is a simple neural network. So we inherit from the NN module all the features of the NN module, and then we have initialization for the constructor, and then there's this forward method that calculates the function. So what does the initialization do? It just produces a key to input two linear layers. So self.fully connected one and self.fully connected two. These are the layers, the linear basically maps. So I pass input dimension, output dimension, the hidden dimension. Say go from input dimension. In this case, input dimension default is 1. So it goes from 1 to 10, and then from 10 to 1. Okay, so it has that two-layer structure that we mentioned. And in the former class, we actually applied the nonlinearity. So I applied it with the connected layer to X, and put it back in X. Apply the loop to X, so this applied in pointwise, we get back X. And then apply the second layer, I get X, and then they go nonlinearity again. Just nonlinearity is like the softmax basically, so we don't need the nonlinearity. So this is often the logic. And then the softmax, if I want to calculate problems, I have to apply softmax. But this is the model. And so is that sort of clear? So this is the neural network. And it has like parameters, and these linear layers have parameters. And for example, if I make maybe a simple model here, you can see I'm going to make a model, simple hidden number of hidden dimension. Okay, I set it to 50. Let's say do 10. Model parameters. So you can see these are the parameters of the model. So it goes from 1 to 50, or 1 to 10, because the other input dimension is 1. So I could do input dimension 1. So you can see the default is 1. So input dimension is 1, output dimension is 1, hidden dimension is 10. So it goes from 1 to 10. So this is the transpose of this, is basically what's specified. Remember, things apply as transpose when you do these linear models. So I have this first layer, and then you have the second layer. So this is the weights, and this is the biases, weights and bias. It has a bunch of parameters initialized in some way. And if I want to plot this, I can, for example, because it's this is a nonlinear one-dimensional function. I'm generating some data from -5 to 5, reaching -1 and 1. So actually, it's better to do view maybe. So it's going to be one-dimensional. It's like basically 100 by 1, and then applying the sigmoid to the output of this is going to be my, for example, probabilistic model that I applied it. So this is one example where we generated like a nonlinear function. This is from the input to the output. This is how it looks like. So this is a one-dimensional function. You run it multiple times, you get different kind of. So this is with 10 hidden layers. You can see this is basically I'm modeling the probability of y, for example, 1 hidden layer. So that's like replaces the logistic regression. In logistic regression, you go from like that or like this, but this can go up and down. If I increase the number of hidden layers, you can see what would happen. Still pretty smooth. These are the kind of equations. So this is kind of like weird thing. So you can see like these are like different, like these are random nonlinear functions that you get because every time I generate one of these, it initializes randomly. So this is my initial sort of class of functions. Okay, you can play with it. Okay. So again, so that's
The reason shape is changing is because your input is changing.
no, yeah, the input is changing and also the model is changing. So I can fix the input if you want. I think the input is not changing because input is with line space -5 and 5. The reason why it's changing, I generate the model again. Every time I generate the model, like create the model, the weights are randomly initialized. So the weights of the layers. Okay, so these are the weights. So every time I run it, for example, I apply I create the model. Implicitly, these linear layers are generated, and these linear layers have these parameters that are automatically initialized. That's
But
it.
in reality, that would reassign based on the data.
Usually, you can do whatever you want, but if you generate one, random initialize, then we train. And when we train, we move the graph, right? That's what we usually do. We'll see. Okay. So this is the initial basically network. And one random example from the class here.
Can you drop what the X and Y axis?
So I'm creating a function that takes the input dimension 1 and output dimension 1. So it's like function from R to R. We have a single function. It's a nonlinear function. Maps R to R. Okay, I'm giving it some values and I'm looking at the output to see what kind of shape it is. Okay, so for example, in the case of it has like a logistic regression, the function that I'm looking at would look like sigma alpha x plus or ax plus b. Okay, that would be the logistic regression function in with feature of dimension 1. So this one is neural network. What it does is exactly what does it do? So it takes x, maps it to input dimension 1, maps it to 50, or in this case 50. How do I map it linear into 50? I need a linear map, so a matrix that maps takes one dimension here and 50 here. So basically, the linear map would be like, in this case, would be just the vector. This W would be 50 by 1, and then plus a B, which is 50 dimensional. And the W in this case, I should transpose the things. Or okay, we don't have to worry about the way that the parameters represent, but that's the first layer. So and then I apply a sigma. That's the redo, and then I apply, because it's 50 dimensional, I go back to 1 dimension, apply another weight here, which is 50 by 1. Okay, this is a new weight, W1. This is B1. This is W2, this is B2. And this is sigma. Okay, so this operation is that linear. So that's we kind of 1 applied to X. Produces this again, and then I can equal to x, and then I apply x equal f dot redo. This is applying this nonlinearity. Okay, and then I apply the second layer, which is like self dot we connected to x. That would be this part, and then the output, this is, okay, so this is maybe redo, that's the redo. The output is really the sigma, which it's not part of the way I define the model. I'm applying it outside here. Okay, so you can put it inside the model if you want, for sigma. Put it in the forward pass, then the model goes from x to something in 0, 1. The way I define it, I go up to this point, which gives me something in R, and I interpret it as the logits or log box. Does that make sense?
So the vertical axis is fx.
Fx, yes, yes.
Horizontal axis is x.
Yeah, yes, yes. X, Fx. That would be in the easier answer. Okay, sounds good. So you can see, like, although I have 50 hidden units, the shapes that I randomly get are not very crazy. There's a bit of, okay, so you get a bit of craziness, but now we're getting a little bit. But oftentimes, there's not much complexity, okay? This is the interesting aspect. There is like a little bit of complexity, but the shapes that you get are fairly simple. Okay. Good. Okay, now we can extend it a little bit. Let's define a layer following the dense layer. So input dimension, output dimension, and some activation. So activation is the function. So this these nonlinearities are called activation. So activation functions. So activation is default. I set it as torch that kind edge, anything else. So fully connected would be a linear layer, input dimension, output dimension, activation would be activation. And then what it does for has apply the fully connected layer, which is just a linear path, and then apply the activation. Okay. So this is a generalized neural network layer, which I'm calling dense, because some people call it dense layer, just fully connected. And then I just want to introduce this idea, which is a simple way of creating these, the composing. You can do this like that. You can just, this is one way of doing it. You can just define these in your initialization and then do the operation in the forward pass. Because I have a very simple, often people do this, they want to do the complicated equations. In this case, I want to basically, let's say, compose these dense layers. There's this NN sequential. So that is probably too fast. In any case, this NN sequential, you pass it a list of like a bunch of modules. Okay, so of the type NN module, basically your bunch and they compose them. They compose, so I create a dense 110, so this goes from 1 to 10, one of these. So it composes it, and then basically what it does is that kind of like cascades them together. It's just a function composition. So my input is going to pass through this, and then through this, and through this, and then sigma. So n sigma is just like the module version of sigma. It's just a single module that just does that. Here. So you can do it with like this f dot from the functional form or the module form. So in any case, this is a neural network now. Okay, so this NN sequential would be a model which is so in this case it will be more complicated. Dense is not defined. So again goes from 1, you can see from 1 to 1. There's a one-dimensional function, but the inside is more complicated. It's like cascaded more of these layers. And I do again, I can plot, and you can see like the kind of shapes that you get. This is with 10H. Okay, and I'm gonna upload it, and you can like have fun just generating. And this, despite being like a lot of, they go to dimension 10 and then dimension 5. The functions you get still are pretty simple. They're non-linear. Occasionally you can see, but when we like the random ones at least are not too crazy. Okay, so that's how you can like introduce more layers. So far so good. It's 2 ways of doing it. Yeah.
These are the decision boundaries, right?
At this point, like in this problem, the decision boundary would be very. But this is like a binary classification would be very tough. Point 5. This is not this. So let's say this is my classifier. I'm thinking of like classifying this one based on one feature. Okay, so if you want to look at the class, like the boundary, so where this hits the 0.5 in this case, it doesn't even hit. Yeah, we need to do a lot more. So they're very strange looking. Yeah, so for example, here, 50. We cut it at 50, anything that's above the 50, which is this very tiny region, we map 1. There is the mapping here. So at initialization, this is the classifier. The maps the tiny region around 0 to 1, the rest is 0. The visitor boundary would be the 2 points. Yeah, here, like despite the complexity, it shouldn't have any answer. Would be like one side would be 1, and the other side would be 0. This complexity maybe matters actually in this case. There's a tiny complexity. So you go like you cut multiple places. So this part would be 1, the other would be 0. This tiny piece would be 1, and then so these are at initialization. This would be very simple. So this would be no different, let's say, than the usual logistic regression. Okay, so this is similar in a sense, like at least the classification boundary wouldn't be different. Okay, good enough. Any other questions? the mechanics of this. So let's now do neural networks in breast cancer data. So again, I have this load breast cancer. It loads the data. This is, if you remember, we just used two features, the radius and texture. And you're going to classify the basically cancers or not. And so we're carrying them into the flow. So X train and X test. So this view is a very useful function. So the view is object as the dimension that we give it is like slightly shaped, but doesn't do anything. Just the same data view it has. -1 here means anything that needs to be here so that the other dimension is 1. So I want it to be like dimension. So for example, if what happens is like Y train would be, you can see the size, it would be like 398 by 1. Okay, so it just flattens it into a make a vector one-dimensionally. Okay. Okay, so what I'm doing here is I'm creating a model. So the input would be two-dimensional because the actually are two-dimensional. So I'm going to create a neural network that takes two-dimensional input, maps it to 10 hidden layers, like 10 hidden units, or like hidden layer with 10 units, and then 10 to 1. And so this is like a binary classification. So we go to output 1, like 1 dimension. Input 2 dimension, and then I have this function plus decision level sets that you have seen before. So this is just plotting the decision level sets of this random initial model. This is a random neural network, so when I create it, it's randomly initialized, and the decision boundaries are completely off. Okay, so these are decision boundaries. So everything here is going to be probably classified as 0. The decision boundary is somewhere here. So initially it's not a good classifier. But there's no reason why it has to be a good classifier because we didn't do anything with the data. We generated the model. I assume the model is going to be eventually a good model, but initially we got a decision boundary. And you can see there is a non-linearity in this function that you can see. They're not moving. So this is the level set of function. So it's a non-linear function. If it was linear, so the level sets would be just lines. So here are the level sets. And you can do it multiple times if you want. But this is a different kind. You can see it's like that. Now you can see like complexity. Even level set. We do it multiple more times. See. So more complicated. So this part and this part would be 0. This part would be 1. Interesting that nonlinear shapes. Okay, then we go. So that's the initialization. I'm creating the same thing here, but I drop the sigmoid. So here I don't want a sigmoid. I want to go all the way to the logits, and then the rest is going to be put into the loss. So the sigmoid is like absorbed into the loss. You get that log loss here. So I'm creating the model. I'm going to show the parameters, and this is the log loss if you remember. So you evaluate the model of the training data, and this is my log. You go back. It's basically picking the labels and the logits. So the Z is the logits. Okay, so case Y and the logits Z in this case. And then I have a train, which I'm going to show you. I pass it the model, the log loss, the number of steps, the learning rate, and an optimizer. And in this case, I'm using this advanced sort of optimizer. So an advanced version of SGD, all the delta results. It's called the Atom. There's another version of Atom with big features of the W. But you can have your own version, like the SGD, or you can run it yourself. But we're going to do this and maybe compare with the SGD if you want. So what did the train do? So I passed it a model, a loss function, number of steps, learning rate, momentum, the optimizer. So if there is no optimizer is none, it defaults to the SPV. You pass it the model parameters, so these optimization optimizers of Torch, you give them parameters. Okay, and if you remember what it does is it takes a step in the directions of the gradient of parameters every time you apply this. If you ever even apply off instead, then takes one step. If I don't, I just initialize it with the optimizer. If the optimizer is passed, it's going to be the optimizer. In that case, we enforce that optimizer at model parameters learning rate. And this is like a loop that you have also every year. So you like iterate through the steps. I compute the loss on the model. Okay. So you pass it the model if you remember. Um, so it takes a model, just evaluates the model, and evaluates the loss of the model. Okay. So I pass it whatever model I want. Calculates the loss. Loss dot backward. What does this do? Calculates the gradient. Gradients of all the parameters that you require the gradient to be calculated. So what are the parameters in the model? The weights and the biases of the hidden layers. Okay, so it's not obvious what they are, but how do we know? So the model has a bunch of parameters. Where are the parameters? The parameters are, so when I create this dense layer, for example, the dense layer has initialization, if you remember. So this was the initialization. So in this initialization, usually you have the parameters. So the parameters are inside this enemy. So if you like unpack it on the linear, define these based on bias. So when I just created this n linear because it has parameters, it's registered as parameters in the model. This activation doesn't have any parameters. So parameters are going to be just weights and biases of this dense layer. And then because we have the sequential, you have two of these, you have two sets of these parameters. So these are all the parameters of the model. When I print it, you can see later that all these parameters printed. So you have these 10 by 2 or 2 by 10 matrices and then 10 by 1 matrices. And so that is known to PyTorch. So when I do loss backward, because the model is applied to the training data and I calculate the loss. So the loss just contains all these parameters. And then in the backward, updates the gradient, you do the optimization step. It moves it like the parameters in the direction of the gradient. And then you zero out something that's zero, it zeroes out the gradient. So if this wasn't familiar, you go back to the previous softmax notebook that we did, we sort of trying to dig into this. Okay. So what exactly, so this doesn't calculate the gradients, so just basic step. This calculates the gradients, this does the step, this zeroes out the gradient. And then you take the history, like report the loss history. And by the end, I don't have to like pass return the parameters because the parameters are just updated in the model. So the model is going to change as I do this. At the end, the model has the right parameters. So let's see what it does. Give you a lot of time. So just very quickly. Okay, so it did some nice optimization. And let's do, so this is like the output result. So you can see they found like nice bounding, very sharp. And so it started from that very, actually we didn't plot this is not the one, but I set the seed such that this would produce, but you start from a random model and then the loss goes down and by the end you get this. So here I'm wrapping it because I'm adding the sigma that I want to go from. So this wrapped model is just log it and then pass the sigma and it's about the decision levels. The decision levels are good, sort of. Okay. Sounds good. We did great in this one on the neural network. Did a lot of hidden units, and you can play with this. You can add like more. So I can, for example, do this. This adds a lot, like another layer in between. You can do like the calculation, and okay, bad things happen at the end. We can see, but interestingly, the output is another. And then you can like evaluate these. So you can evaluate which one is better. But it's sort of finding the different boundary. Every time you do it, It's gonna be a different thing, and then for different models, you get different. So maybe next time we'll come back and elaborate a little bit on this, and then maybe talk about it a little bit. Sounds good? Thank you, guys. See you next time.